Everyone, today I will solve with you two different examples about bubble point and dew point calculations for both temperature and pressure. It will be two simple examples. It will not be complicated, just using the basic equations for these kinds of calculations. So, starting with example 1, a Viber mixture containing N-hexane mole fraction of 0.15 and N-octane mole fraction of 0.5, and the balanced air is at 100 degrees Celsius. In part A, they are asking us what is the dew point pressure. So we need to find the dew point pressure. And to make it easy for me and for you guys, I already wrote here all the equations that I'm going to need for this example. So I will not go back and forth to make sure that I wrote the right equation. And as you see here, I already wrote the givens, N-hexane 0.15, N-octane 0.5, the air 0.35, and the temperature 100 degrees Celsius. And of course, if you are an engineer, you know that if we are going to calculate the saturated pressure, we always use Antonius equation, which is a function of temperature and constants. And this, so I already also found from my reference the constant values for A, B, C, which we are going to use in Antonius equation. Of course, these values may differ. You might not get the same exact values, but it will not be that different values from different references. So let's start by calculating the saturated pressure by using this equation, which is the Antonius equation, which is 10 to the power of A minus B over T plus C. So I need to apply this equation for both N-hexane and N-octane. First, starting by the N-hexane, 10 to the power of A minus E over T plus C. Make sure to close all the brackets. And we got our answer. I will just drag it for N-octane because nothing. When you drag it, it will already use these values. But I just need to make sure that I choose the right cell for the temperature, which is the 100 degrees Celsius. And here I got both the saturated pressure for N-hexane and N-octane. Now, since we already have the saturated pressure, we can calculate the dew point pressure because it's only a function of the mole fraction and saturated pressure. So it will equal 1 over Y of the hexane divided by the saturated pressure of the hexane plus Y of the octane divided by the saturated pressure of the octane. Close all the brackets, and you will get your dew point pressure for this mixture of gases. And now I want to find the x's for both components using this equation, which is function of Y, B dew, and the saturated pressure. So for the first one, it will be Y for the hexane multiplied by the B dew divided over the B saturated for the hexane. Close all the brackets and you got your value. Drag it and make sure that you choose the right cells. For example, here it will be this one, and for the B dew it will be this one. And by this, we finished part A, as simple as this, as simple as it is. And for part B, it's asked at given a pressure of 760 millimeter mercury, find the dew point temperature. So here we need dew point temperature. It's very simple. It is even simpler than the part A. So here we already have the pressure given, which is 760 for both components. We need to assume the due temperature. For example, I will write 100, any number. You can choose any number. Now, using this number that you assumed, you need to calculate the B saturation using Antoni's equation for both components again. So it will be just 10 to the power of A minus E over T that I assumed plus C. Close all the brackets and you will get your value. Drag it and make sure that it's selected for you the right cells for all of them. Of course, the temperature is not right. Here we go. Now it's perfect. Okay. So now we found the saturated pressure. If you notice, it's the same answer, same answer as example part A, because we used the same. I assumed same temperature. Of course, it wasn't. I didn't mean to, but let's go with it. Now for the PDU calculations, also I will use the same equation that we have here. This equation. Okay, I did something horrible. Let's just delete this. Okay, it will be 1 over y of the hexane, sorry, over the B sat of the hexane that you found, plus y of the octane over the B sat that you found according to the assumed temperature. Those are the brackets and you will get your value. Now, how I'm going to find the right dew point temperature? I will find the differences between the B given that they gave it to me and the B due that I found from my equation, and I will get the squared because if we get we make sure we don't want a negative value, and then I'm going to use something called solver. So let's find out first thing the differences, and then I can show you the solver. Will be B given minus B due found squared. So this is the difference. Now, of course, if you are, as I said, if you are an engineer, I'm sure you already deal before with solver. You find it in data, solver. Your set object is the difference cell, because you want to make it minimum as minimum as possible by changing the temperature cell. And now you put solve and you will find your value to be 104.23, which is the right answer. So in this now we already finished part B and part A, and of course you can pause the video to compare the numbers, my numbers with your numbers. Now let's move to the next example. A liquid mixture containing N-hexane mole fraction of 0.15 and N-octane mole fraction of 0.85 at 100 degrees Celsius. What is the bubble point pressure at a given? What is the bubble point pressure? So for part A, we need to find bubble point pressure. As I did before, I already wrote all my givens here. I have my constants here, and we need also at the beginning, we need to calculate the B sat. As you see, it is the same temperature, so it will give me the same answer as before. So let's do it again. 10 to the power A minus P over T plus C. Close all the brackets and get your answer. Drag it and make sure to change the temperature. Okay, now for calculating the bubble point pressure, we have this equation, which is a function of the saturated pressure and the mole fraction of the liquid. So basically, it will be the summation. As much as components you have, you need to add them together to get your answer. So it will equal, let's just start with the hexane. X of the hexane multiplied by Esat added to X of the octane multiplied by Esat of the octane. And we got our value, which is the asked value, as you see here. And now we can find the mole fraction of the gas using this equation that I wrote here. Will equal to X of the hexane multiplied by saturated pressure divided by the bubble. Same thing for the octane. It will be X of the octane multiplied by the saturated of the octane divided by the bubble that you found for this mixture. Okay, so these are my values, and by this I ended the part A. And now for part B, at a given pressure of 760 millimeter mercury, what is the bubble point temperature? Bubble point temperature. So similar to the last example, we need to assume here a number, then we are going to use to calculate the difference, and then we are going to use the solver to get the right value, because solver is do for you trial and error. So if you are going to do it with your hand, you might even if you do it more than one time, you might not get the most accurate value. But here, because it's a computer, it's a machine, it's already do all the calculations for you. And it's an easy tool, so why don't use it instead of using hand calculations? Of course, if you are in an exam, you have to do it using your hands. But here now we are learning how to use a simple tool to make your life easier as an engineer. So for T bubble, I will assume also 100. And I think I need to change this number because I always assume 100. Okay, I will make it 150. Show you that whatever value that you assume, and then you will get the right answer. Okay, let's put it 100. Okay, sorry. Let's put it 100. What's wrong? Let's put it 150. Okay, now we calculate the Psat. It will equal 10 to the power A minus C over C that I assumed plus the C. Closing all the brackets, and you got your value. Just drag it and make sure to change the cells that need to be changed. For example, I just need here to change the temperature. And by the way, I don't write the temperature twice, because when you are going to use solver, you need the set object cell. It will be only one. I never tried it with two cells, but so by changing this cell, it will change directly these two answers. So this way it's easier for me. I don't know if I can do it for both cells. I never tried it before, but do whatever you think is easy for you. That's the beauty of having such a wonderful programs. Okay, now for the bubble point calculated using this equation, the second one, it will be the summations as I mentioned before. It will be X of the hexane multiplied by the Psat that I found at the temperature that I assumed, plus of the octane multiplied by the P-sat2. Okay, so now I found the bubble point, and I need to get the difference between the B bubble that was given and between the P bubble calculated. Of course, squared, as I mentioned, because if it is an positive value, I want to get rid of it. Okay, so I got this value. Now, data, solver, state object is the difference object. Of course, minimum by changing the T bubble cell. Okay, let's do it. I got 109. Let's check if my answer is right because I already did it here before. It is right. So as you see, this is our final value for part B. It is very simple kind of calculations. Of course, you can have more than two components, and it will be a little more complicated, but by the end it is the same equations. So make sure to memorize these equations, and I think you will be in the safe side. And thank you for listening to the end of the video. I hope this video is benefit. This video was made for the purposes to make sure that the students will understand the basic of calculations for the bubble and dew point pressures and temperatures. And it was a group work recorded by me, and we are a chemical engineering team from UAE University in Al Ain, UAE. And thank you very much. I hope you will have a great year, and good luck for our future engineers.